Welcome to VizConnect, connecting you with the art of data visualization and storytelling. My name is Sagar Kapoor, part of customer success team at Tableau, and welcome to the season 4 of VizConnect. So all the sessions which are presented in VizConnect are uploaded to our YouTube channel. Go ahead, subscribe to it. Some great content is waiting for you. Today only I have uploaded our VizConnect Data Doctor session by the Tableau Zen Master Jim Dinner on table calculations. Go ahead and watch it. Some great tips and tricks on where you should go ahead and how you should go ahead and use table calculations. We have a LinkedIn group. Go ahead, uh, join the group, connect with fellow data fans, and learn from each other. And also, the Tableau conference is back. So we will have a Tableau conference in May from 17 and 19. So it will be a hybrid in terms of in-person and virtual. I am excited about it, and I'm sure you are also excited about the conference. With that, let me go ahead and introduce our speaker for today. Brian is a senior data visualization and analytics consultant at Clear Intelligence, our Tableau public ambassador, a co-lead for the Boston Tableau user group, and a co-lead for the SDG Viz project, and a co-author on domorewithdata.com and general Tableau fanatic. Brian loves to help others leverage the power of Tableau to get the most out of their data, both as a consultant and through his work with the community. Today, Brian will go ahead and talk about fun with curves in Tableau. So without further ado, Brian, over to you.
Good morning, everybody. Thank you for that introduction. Let me just share my screen. All right, so hi everyone, my name is Brian Moore, and today we're going to be talking about a topic that may not have too much use in the workplace, but it's something that I really enjoy, and that's building curved elements in Tableau. So hoping to make this presentation somewhat interactive, so if you'd like to follow along and kind of build these curved things along with me, just go to domorewithdata.com. Click on the resources tab in the top right corner, and then click on that first link. It says Fun with Curves in Tableau - presentation, workbook and data. And there you can download the sample workbook. You can also download the sample data that we're going to be using, but the workbook should have everything you need. It already has all the data sources built and embedded. All right, so won't waste any time on the bio here, since Scott already gave me a pretty good introduction there. So we'll just move right along. All right, so think about some of your favorite pieces of data art. So I'm willing to bet that most of them contain some type of curved element, and there are a couple of reasons why that's usually true. So first, there have been scientific studies that have proved that when it comes to art, humans prefer curves over straight lines and corners. And there's also that wow factor. So as we all know, curves don't exist in Tableau. They take effort, and a lot of people just don't know where to start. So this is a good place to start. So we're going to walk through the technical process of building these curved elements, from densifying your data all the way up to building your views. And we're going to focus on three types of curved elements: so circles, Bezier curves, and sigmoid curves. You can also find all of this information. This presentation is based on a series of blog posts on Do More with Data called Fun with Curves in Tableau. All right, so to build any kind of curved element in Tableau, you first need to densify your data. So I'm sure you've probably heard the term, and if you don't know what it means, it's basically just creating additional data points. So imagine you have a data source with 3 rows, but you need additional data points to draw the curved lines or to make some polygons. We can do what's sometimes called a Cartesian join or a cross join to a densification table. A densification table is typically just another table that has some number of records. And the result of that cross join or a Cartesian join, if you were to join these together, so starting with 3 rows, if you join to a densification table with 5 rows, the result in your data source, you'll now have 15 rows. So for this row 1, we now have 5 rows with points 1 through 5. For row 2, we now have 5 rows, 1 through 5, and for row 3, we now have 5 rows. So we started with 3, joined to a densification table, and now we have 5 times as many records in our data source. And we can use these additional points in our calculations. So to do that join, if you go to your data source, double click to go into the physical layer. So here's our source data here. We have our circle data, and then we have our densification table. And we're going to just join those with the join calculation. So on both sides of the join, we're going to use join calculation and just put a value of 1. Really, you can put anything here as long as these values are the same. So there are a few things to keep in mind when you're building your densification table and choosing how many rows to include. So if you have too many rows, you might be hurting performance as you're significantly increasing the size of your data source. Because remember, however many rows in your densification table, your base data is going to be multiplied by that many rows. But on the other side, if you have too few rows, then your curves won't look smooth, they'll look kind of jagged, and you'll see the lines and corners. So here's just a quick demonstration of how the number of rows can affect the shape of your circle. So obviously you can't draw a circle with 1 point, you can't draw one with 2, with 3 you get a triangle, and so on. And you can see the more points that we add, the more our circle starts to take shape. So when you're drawing curves in Tableau, you're not actually drawing curved lines. What you're doing is just drawing a series of straight lines. And the more points you have, the smaller those lines are, and the more curved your elements become. So you can see even with 50 points, you can still see a little bit of the jagged edges there. All right, so that is a good segue into our first curved element type, which are circles. So you may be wondering why you would ever need to know how to draw a circle in Tableau when Tableau already has a circle mark type. And that's a fair question. But the calculations needed for drawing a circle are the exact same calculations needed to build any type of radial chart you can imagine. So this is more about learning the technique so you can apply it to your own custom charts and less about drawing actual circles. Though I do use this technique pretty frequently on Tableau Public to draw circles when the exact size is important. With all of the sizing options in Tableau, you can change the range and all of that. It's pretty easily for the size to lose its meaning. But with this technique, you can ensure that the sizes of your circles are accurate and meaningful. But again, I would never do this in a business dashboard. All right, so if you downloaded the sample workbook, I've already built all of the data sources, but here's a look at our sample data. So our kind of source data has 10 records that we're going to use to draw 10 individual circles. And we're going to use a densification table with 50 points. So our densification table is just one column called points with records 1 through 50. Once you have your data source built, there are really only 2 things you need to know to draw a circle. So there are only 2 inputs. You need to know the distance of each point from the center of the circle. So that's this blue line here. So you need to know that distance. And you need to know the position of each point around a circle. We'll talk more about that in a second. So for our circles, we want the area of the circle to represent the value in our data source. So if you look at our data, we have this value column. So we want to use this as the area of our circles. So to do that, we can calculate the radius using this calculation here. So it's just the square root of the area, which in our case is value, divided by pi, and that'll give us the length of that blue line. The second input is the position around the circle. So imagine you're looking at a clock. So 3 o'clock would be 25% around the circle, 6 o'clock would be 50% around the circle, 9 o'clock would be 75% around the circle, and then 12 o'clock would be 100% or one full loop around the circle. So this position field it's going to be a percentage from 0 to 100% that represents how far around the circle that point should appear. And to calculate this, we're just going to divide our points field divided by the maximum value in that points field. So if we look at our data again, so for 0.1, it would be 1 divided by 50, or 2%. For 0.2, it would be 2 divided by 50, or 4%, 6%, 8%, and so on. So if you see here, we'll have points, this is cut off, we'll have points 1 through 50 at every 2% increment. So once you have those two inputs, all you need to do is plug them into these equations here to get x and y. So here's our x calculation. We can just plug in the radius and the position, and our y calculation, where again, we'll just plug in the radius and position. So if you've downloaded the workbook, I've already created all the calculations. Just click on the Circle Demo tab, and then on the Circle data source up here. And we're going to right click on X and drag that out to columns. So right clicking and dragging out your fields will let you choose the level of aggregation before anything is actually rendered in the view. We want to bring it out with no aggregation because we want to see every individual point. So I'm going to select that top option there. Then I'm going to do the same thing for Y. And then I'm just going to filter on one of our circles for now. All right, so now you see we have 50 points that are plotted around a circle. If I bring out the position field on the labels, just going to make that a percentage. You'll see our first point is 2% around the circle, 4%, 6%, and then all the way around the circle. And the distance from the center here to each point is calculated from our radius. So if we were to bring our radius out, see the radius is 4.029, and if you look at these points that are coming straight out from the center of the circle, you'll see they are just outside of 4. Let's pull those off. We'll pull this filter off. All right, now to turn these plots into circles, we're just going to change the mark type to polygon. We're going to drag our circle ID onto color, which is going to kind of partition our data. And then we just need to tell Tableau how to connect our points, which we're going to do with our points field. So again, if you look at our points, this has values 1 through 50, and that's the order of the points around the circle. That's how we want Tableau to connect them. So I'm going to right click and drag that to path. And there we go. So just looking at this quickly, you're probably thinking two things. One, these look more like ovals than circles. And two, it looks like there's only 2 circles there. So the reason they look like ovals is because in this worksheet, in the view, the pane is wider than it is tall. So anytime you're placing a radial chart on a dashboard, it's important that you set the height and the width equal. And you may even want to fix the X and Y axis so they're the same, so you can ensure that your radial chart is actually a circle. And that some of the values aren't getting skewed because it's wider than it is tall or taller than it is wide. And second, the reason that you see 2 circles is because right now all of these circles have the same starting point. They're all starting at 0, 0. So they're currently all stacked on top of each other. But if I click through these, you see that we actually do have 10 circles, just not all of them are visible. So there are a lot of different things you can do to kind of spread these out. Like you could just drag circle ID onto rows and create 10 different panes. You could drag that out into columns, you get the same thing. But what I like to do is I like to have everything on the same pane. It gives you a lot more control of exactly where everything is being placed. So what we're going to do is use an offset value to arrange our circles. And that's going to use this circle spacing parameter up here. So this is just a numeric parameter. Right now I have it set to 10. And we'll create a calculated field called circle spacing. So our circle spacing parameter times our circle ID. So if we look at our data, so the value for this first row is going to be 10, be 1 times 10, 2 times 10 would be 20, 3 times 10 would be 30, and so on. So if we were to add that to our X calculation. We now have a row of circles. And the way this works is essentially for this first one, it's moving every one of our points 10 to the right. For the second one, it's moving everything 20 to the right and so on. But the way that I like to think about it is rather than moving everything, is that we're creating just a new starting point for our circles. So instead of this circle starting at 0, 0, it's now starting at 10, 0. And this one's starting at 20, 0. This one's starting at 30, 0. And then the circle is being built around that. So it's essentially the same thing, but thinking about it as creating a new starting point may help with some of the more kind of complicated applications for this. Okay, so I'm just gonna remove that. Oh, just gonna remove that from my X calculation real quick. Okay, so if you're to add that offset value to X, then you'll end up with a nice row of circles. If you add it to Y, you'll end up with a nice column of circles. And if you were to add it to X and Y, you would end up with a diagonal line of circles. So those are a couple different ways to place your circles in a line. But here we're talking about circles. So let's plot our circles in a circle. So to plot these circles around a circle, we need to figure out what values to add to our X and Y coordinates to create our new starting points. So we have 10 circles that we want to plot, and we want to plot those in a circle. So we can use the same calculations that we used before to find that new starting point for each one of those circles. Once again, we just need two inputs. We need the distance from the center of the circle, or the radius, and the position around the circle. So in this case, the radius can be constant. It's not representing any value. We want it to be the same for every point, and we can make it, make the circle however big or small that we want. So what we're going to do is use a parameter, and that way we can also make it dynamic. So for the distance from the center of the circle, we're just going to use this parameter called base radius. And for the position around the circle, so previously to draw each of our individual circles, we were plotting 50 points, and those were from our circles data. So we were taking 1 divided by 50, and this was at 2%, 4%, 6%, etc. But now we don't want to plot these points around the circle. We want to plot these circles around the circle. So it's the same approach, except now we're going to use our circle ID field, and it's going to be 1 divided by the max value, which is 10. So this one would be at 10%, 20%, 30%, 40%, and so on, all the way to 100%. So that's the circle ID divided by the maximum circle ID. And once we have that, the calculations for X and Y are exactly the same. We're just going to plug in our base radius and base position. And we'll call these base X and base Y. Now, if we go back to the worksheet, if I was to just plot those base X and base Y values that we just calculated, so these are our new starting points, you'll see that we have 10 points around the circle at 10%, 20%, 30, 40, 50, and so on, all the way around to 100%. Now, all we need to do is adjust our X and Y calculations that are drawing these circles, and we'll just add our new starting points. So to X, we're going to add base X, and to Y, we're going to add base Y. There you go. Now we have a circle of circles, or all of our circles plotted around a circle, and the circle has a dynamic radius, so you can use this to make these appear bigger or smaller. And there we go. Yeah, so the main takeaway from this section is to build any kind of radial chart, really anything you can imagine, you really just need two inputs. That difficulty for calculating those inputs will be different depending on what you're trying to do, but the inputs will always be the same. And those are the distance from the center and the position around the circle. All right, so now on to our second type of curved elements, Bezier curves. And remember, if you don't catch everything today from this quick run through, you can always learn more about these techniques on Do More with Data. So there are many types of Bezier curves, and they can really vary in complexity, but today we're going to focus on quadratic Bezier curves, which have 3 control points. So an easy way to think about these control points are that there is a starting point, there is a midpoint, and there's an endpoint, and these 3 points create a circle. And the shape of sorry, not a circle, these 3 points create a triangle, and the shape of the triangle will kind of dictate what that curved line looks like. So the starting point and the ending point are simply the start and end of the lines, and then this third point is really going to shape the triangle and ultimately the curve. So in these 4 examples, all 4 of the lines have the same start point and the same end point. They all start at 1, 0 and end at 10, 0. But because of the varying midpoint, they have, pretty, pretty different looking curves. So this one is pretty uniform and tall. Here we have it skewed to the left because our midpoint is to the left. Now it's skewed to the right because our midpoint is to the right. And here it's still uniform, but it's shrunk because our midpoint is lower than in our first example. So in most applications in Tableau, we're going to be dealing curves like we see in example 1 or example 4, where the midpoint is exactly halfway between the start and end point, which creates an isosceles triangle. And for this presentation, we're going to focus only on example 1, which is an equilateral triangle, meaning all 3 sides have the same length. So again, if you've downloaded the workbook, I've already built all the data sources for you, but here's a look at the data we'll be using. So we have 10 rows of data that we'll use to draw 10 curved lines. We have starting and end points for X for each of our rows. We have our X start and X end. And for all of our Y values, we're just going to use 0. So all of the lines will start and end at 0 on the Y axis. And for our densification, we're going to use the same table as we did in the circles example, with just one column called points and values from 1 through 50. All right, so now for our inputs. As I mentioned before, we're building Bezier curves that have 3 control points. Our data source has the coordinates for 2 of those 3 points. So if we go back and look at our data, we have our starting point. So line 1 is starting at 1, 0, and our ending point. So line 1 is ending at 10, 0. So line 2 is starting at 3, 0 and ending at 15, 0. Line 3 is starting at 4, 0, ending at 7, 0. So for each of our lines, we have 2 of the 3 points that we need. We really just need this midpoint. All right, so because we decided to use equilateral triangles, we can calculate that third point pretty easily. So for X, the value is just going to be exactly in the middle of the starting point and the end point. So in this example up here, the triangle is starting at 0, 0. It's ending at 10, 0. So the value for that midpoint, or the X value for the midpoint, is 5, which is exactly between 0 and 10. So you can calculate this for all of your lines by adding the X value or the X start value and the X end value together and dividing by 2. So that would be 10 plus 0 divided by 2 would be 5. So our X value for this third point is 5. And now for Y, we need to calculate the height of the triangle. So we know that all sides are going to be equal because this is an equilateral triangle. So we can calculate the length of any side by subtracting the starting value, the starting X value from the ending X value. So in this example, that would be 10 minus 0. So we know that the length of all 3 of these sides is 10. Now we can just plug that into the formula for calculating the height of the triangle, which is the length of any side times the square root divided by 3, and that'll give us the Y value for the midpoint, 8.67. So for this example here, for this triangle, our 3 points are 0, 0, 5, and 8.67, and 10, 0. And if you use both of these calculations in your data source, you'll now have those 3 sets of coordinates for all 10 of your lines. So if we were to stop here and plot each of these points, we would have 10 equilateral triangles of different sizes and starting at different points along the x-axis. All right, so now to turn these triangles into curved lines. So we just need a couple more calculations. So we've already calculated our 3 sets of points. The next thing that we need to calculate is t. And think of t similar to the position field that we calculated in the circle examples. It's going to be a percentage value that we're using to evenly space points along our line. Similar to in the circles, we were using the position field to evenly space points around a circle. The only real difference is here we need the value to start at 0 and end at 100%. Whereas for the circles, it was okay that it started at a value greater than 0%. So to modify this calculation, we just subtract 1 from the numerator and the denominator. So if we're looking at our data, so for point 1, it would be 1 minus 1 equals 0, divided by 50 minus 1 is 49. So it'd be 0 divided by 49 is 0. 1 divided by 49 is, I'm not sure exactly what the value is, but all the way down to 49 divided by 49 will give you 100%. So this would start at 0% and end at 100%. Now, once we have t and we have our 3 inputs, we can just plug those into the x and y calculations. So you see that these calculations are exactly the same, except x uses the 3 x values, x start, x mid, and x end, and y uses the 3 y values, y start, y mid, and y end. All right, so now if we right click and drag out x, and then drag out y, you can see each of our points plotted along these curves. Now we just want to turn these into lines, and we'll drag our line ID onto color. And now we have our 10 curved lines. You could even turn these into polygons and get this nice looking kind of like rolling foothills. So in this example, we didn't put anything on path, but anytime you're working with lines or polygons, it's important to let Tableau know how to connect those lines, even if it works without them. Because once you start adding more to this view and it gets more complicated, Tableau might not be able to figure that out on its own. So we're going to drag our points field to path. That doesn't change our view, but it's still kind of a best practice to do that when you're working with lines and polygons. All right, so this is a relatively simple example, but now let's take what we learned here and combine it with what we learned in the first section. And the result should look pretty familiar. So first, we're going to take our x values and we're going to plot those around a circle instead of a straight line. So we know from that first section that in order to plot points around a circle, we need 2 inputs, the radius and the position around the circle. For the radius, we want all of the points to be equally distanced from the center, so we can just reuse that base radius parameter that we used in the first example. And we'll just use that again. The calculation for the position around the circle is a little bit trickier this time. So we need to know the maximum x value, but we have 2 x columns. So let's go back and look at our data. We have an x start column and we have an x end column. So in this example, all the lines are going from left to right, meaning the x end is always higher than the x start. So if that is the case, we could just take the maximum value of this x end column, but let's not assume anything. In some examples, there could potentially be lines that go from the right to the left. So we want to get the maximum value of both of our x columns. So here we can use this max point calculation. And what this is doing, so the inside section of this calculation, for each row, it's just taking the maximum value of the start and end x fields. And then that's wrapped in a level of detail calculation, which will give us the maximum value of this for our entire data source. So if we look at our data, we'll see the maximum value in any of these fields is 15. So this max point here would return a value of 15. All right, so now we need to plot both our starting points and our ending points around the circle. So we just need to calculate that position field for both. So to get the position for the starting points, it's just the x start divided by that max point. And to get the position value for the end point, it's just the x end divided by that max point field. All right, so let's take a quick step back. So to draw these curves, we need three sets of coordinates to draw the curved line, or the Bezier curved lines. We need the coordinates for the start of the line, the coordinates for the end of the line, and the coordinates for the midpoint. Lucky for us, a circle has a very convenient midpoint that we can use for all of our lines, and that is 0, 0. And we'll talk about that more in a few minutes. So we really just need to calculate the other two sets of points, and we've already calculated the inputs for those. We already have the radius and we have the position fields. So to get the coordinates for our starting point, so that first set of coordinates, we'll call them circle x start and circle y start. We're just going to plug the radius and the position fields into our circle calculation. This will give us our first set of coordinates. We're going to do the same thing for the end points, except we're going to use the position end field instead of position end. So at this point, we now have three sets of coordinates. We have our starting coordinates, which is circle x and circle y start. We have our midpoint coordinates, which are 0, 0, and we have our endpoint coordinates, which are circle x end and circle y end. And then we can just plug them into the same calculation that we used before for the Bezier curves. But here we'll call them circle x and circle y. So now if I replace x and y with our circle x and y fields, we now have the foundation of a chord chart. So this chord chart uses the same exact calculations as the first example with the Bezier curves. We just used a little bit of additional math to calculate the coordinates for the start and end points. So for example, in line 2, let's look at the raw data. Line 2 went from 3 to 15 along the x-axis. So it went from 3 to 15, and we calculated that midpoint using the first set of calculations. In our next example, it was still going from 3 to 15, and then we just used 0, 0, the center of the circle, as our midpoint. So in the first example, it went from 3 to 15. The second example still went 3 to 15, but instead of those points being on a flat plane, we took those points and wrapped them around a circle. So you can calculate the coordinates for those three sets of points in a lot of different ways. It really just depends on your use case. And then it's just a matter of plugging those three sets of coordinates into your x and y formulas. All right, so now on to our third and final type of curved element, and this is a sigmoid curve. So whether you know it or not, these type of curves are everywhere on Tableau Public. So Sankey diagrams, curvy bump charts, the dendrograms, the curved lines on a map, they all use this same type of curve, and they're all created in very similar ways. So we're going to cover a few examples here, but the same technique can be applied to really an endless number of custom chart types. So we're going to cover two different models for building sigmoid curves. We'll call them the standard model and the dynamic model. So think about most types of charts that use sigmoid curves, and they have something in something in common. The start and the end of the lines are uniform. So if it's going from left to right, they all start in one column and they all end in another column. If they're going from top to bottom, they all start in one row and they all end in another row. So in most use cases for sigmoid curves, this is true, but there are some cases where it may not be true. So if either of these aren't true, so like for this example, they all start in a uniform column, but they end in different columns. So if either of those aren't true, if they either start or end in a different column, then we're going to use this dynamic model. So let's start with the standard model. All right, so here's the data we'll be using for our first example. So we have 12 rows that we use to draw 12 curved lines, and each of our lines has a starting position and an ending position. I know we've used the term position in previous examples, but here think of it as kind of like a ranking. So a position of 1 would be at the very bottom, a position of 2 would be right above that, position 3 right above that, all the way up to you reach your max position. So here it's kind of the vertical position. You may notice that the densification table looks a little bit different. So instead of just a single column of points, we now have 2 columns. We have T and path. So the path field is just going to be used to tell Tableau how to connect the points. So connect the dots. And the T field is going to be used to draw the curve, and it will be a value evenly spaced between -6 and 6. So for our example, we're going to use 25 points, and we're going to have a value at every 0.5 increment. So -6, -5.5, -5, and so on. You could also use 50 points for a smoother curve and have a value at every 0.25 increment. Really, you can use however many points you want. You just have to do the math to evenly space them between -6 and 6. And why -6 and 6? I have no idea. All I know is that those values are needed for the sigmoid calculations to function properly. So to build our curved lines, we only need 2 calculations. First, we need the sigmoid function, and this calculation will never change. This is always going to be the same for all of our examples. And second, we are going to use our starting and position fields from our data source along with that sigmoid function to calculate our curve values. So essentially what these calculations are doing is they're calculating the total vertical distance that needs to be traveled, so the end position minus the start position, then multiplying that by the sigmoid function to space the points out appropriately to get that nice S-shaped curve. So let's just build our curves and then we'll come back to this curve calculation. So if you're following along at home, just click on that Sigmoid Demo Slope Chart tab, and then on the Sigmoid Data Slope Chart data source, we're going to right click and drag out T. Then we'll right click and drag out curve. Drag line ID to color. We'll change this to a line. And there you have it. With just those 2 calculated fields, we drew these nice 12 curved sigmoid lines. And again, we don't have anything on path here and it's still working, but just general best practice, I'm going to drag our path field on the path to tell Tableau how to connect these points. All right, so now let's go back and take a closer look at how those calculations work. So our sigmoid calculation is a mathematical function with values ranging between 0 and 1 based on this t value. So this table shows the sigmoid value for each t value in the first row. And in the second row, it shows the difference from the previous value. So you can see at the beginning and the end of this line, the sigmoid value does not change very much from one step to the next. But as it approaches the center, that change gets much more significant. So it starts changing a lot more rapidly until it reaches the center, and then it starts going back down. And at the very center, sigmoid equals 0.5, and we'll come back to that in a minute. So if we look at that in context with our lines and our curve calculation, notice that the vertical position of our points doesn't change much at the beginning and the end of our line, but as it approaches the center, it changes much more rapidly. And at the very center of our line, the point is exactly halfway between our starting position and our ending position. So if we were to throw all of this into our curve calculation, so let's calculate the curve value where t equals 0. So that has the sigmoid value of 0.5. So that's our starting position, 4, plus 10 minus 4, which is the vertical distance, times sigmoid, which is 0.5. So that's going to be 4 plus 3 equals 7. And now if we look at our line where t equals 0, the vertical position equals 7, exactly halfway between our starting point and our ending point. We can do that with another example. So let's do it where t equals -3. So where t equals -3, the sigmoid value is 0.047. Again, we'll plug that into our same calculation. So our starting point 4 plus 10 minus 4, which is the vertical distance, times the sigmoid value would be 4.28. And if we look at our line, where t equals 3, it's just above 4 and a quarter of the way to 5. So exactly 4.28. So that's how these calculations work. Let's look at a couple more examples. So in our last example, all of our lines had different starting positions and different ending positions, creating this kind of curved slope chart. But what would happen if all of our lines had the same starting position? So for this example, I have a parameter called sigmoid start, and we're going to use that instead of our starting position field. So everything else is going to stay the same. Just imagine in our data source, here's our data. Instead of this starting position field here, it just has a constant value. So I created another curve calculation. It's exactly the same, but instead of using the start position field, we are using that sigmoid start parameter. And if I drag that to curve, now we have a curved dendrogram. And because we used a parameter, the starting point for that can be dynamic. You can put that wherever you want to kind of fit your design. But if you have it exactly halfway between the minimum value and the maximum value, it'll give you that kind of nice, evenly shaped dendrogram. Similarly, you could have the same ending point for all of these, and then you could have them all go down to a single point on the right, which would be kind of the same as just reversing this. All right, so now on to everyone's favorite, Sankey diagrams. So this isn't going to be an in-depth tutorial on how to build Sankeys. People much smarter than me, aka the flailolages, have written a ton of blog posts and shared a lot of templates if you're interested in building one. This is just going to be more about, taking what we've learned so far and seeing how it applies to building a Sankey. So kind of understanding the mechanics of a Sankey diagram. So the main difference between the other Sigmoid examples and what we're going to do now is the mark type. So instead of using lines, we are now going to build some polygons. So basically what we need to do is draw two curved lines instead of one, and then connect those lines together. So when you're thinking about this, think about it as two unique lines using the same process as we did in previous examples. So we're going to have a min line, which is going to be the bottom line. We're going to have a max line, which is going to be the top line. Those lines are going to move together, and then we're going to change our mark type to polygon to connect them together to create a solid shape like you would see in a Sankey. So this is going to be a very simple example. So normally you would use like table calculations in Tableau to determine the positions and the widths of each polygons. But we're going to keep it really simple and just use values from our data source, and we're going to make them all the same thickness. So really what we're building is kind of more of like a Sankey slope chart. So here's our data. We have 6 rows that we'll use to create 6 polygons, and we have the starting and ending position for each. You may notice some differences in our densification table here. So we still have the T field, we still have the path field. Those are the same as our previous examples, but we now have this side field. So we have 25 records where the side equals min. We'll use those to draw the min line, which would be this bottom line here. And we have 25 records where the side equals max, and we'll use those to draw the max line. And if you look at the T field, you'll see that it still goes from -6 to 6 on the min side, but then it reverses order and goes from 6 to -6 on the max side. And that's really important, and we'll see more about that in a few minutes. And then our path field is just a sequential number going all the way from 0 to 49. All right, so for our inputs, we need the starting and the end position. We're going to use these to draw our midline, just like we did in previous examples. And we also need the maximum value. So we need some values to draw our max line, which in this case, we're just going to make everything equal thickness. So for our max line values, we're just going to add 1 to our midline values. So let's go back to our data for a second. So on line 1, for our midline, it's going to go from 0 to 2. Our max line is going to go from 1 to 3. For line 2, our midline is going to go from 1 to 4. Our max line is going to go from 2 to 5. So they're going to be uniform and the same thickness for all of our lines. And then we also need sigmoid, which the sigmoid calculation, as I mentioned before, is always exactly the same. So let's take a look at the curve calculation. So at first glance, this may look complicated, but it's almost identical to the calculation we used in previous examples. When we connected to our densification table, we basically created 2 sets of points, one for our min line and one for our max line. And those are segmented with that side field. So in this calculation, if that side field equals min, then we're just going to use the same curve calculation as we did in previous examples. It's going to be the start position plus the end position minus the start position times sigmoid. If the side field does not equal min, so if it equals max or any other value, then we're going to use that same calculation, but instead of using the start position and end position, we're going to use the start position max and end position max fields, which are just these plus 1. So with this calculation, it's going to draw a min line using the values of our data source, and then a max line, which follow the same path, but will just really just be moved up 1 position. All right, so let's start building our curves. So if you're following along at home, just click on the Sigmoid Demo Sankey tab, and then click on the Sigmoid Data Sankey data source. We'll drag T onto columns, drag curve onto rows. For now, I'm going to put side on detail. I'm going to drag line ID to color, and I'm going to make this a line. All right, so this is looking pretty good. So for each of our lines, we have 2 lines that are moving together from left to right and just separated with a thickness of 1 unit. All right, so the next step would be to connect these lines together to create just a solid shape. And to do that, we're going to change the mark type to polygon. So let's do that. So we'll change that to polygon, and that doesn't look right. So because we have the side field on detail, Tableau is treating each one of our lines as their own polygon. But what we want to do is we want to create a polygon with those 2 lines together. So removing that side field should work, right? Well, that's not much better. So remember earlier when I mentioned that working with lines and polygons, you should always address the path field on the marks card, even if your visual works without it. So that's what's happening here. So let's take our path field, right click and drag that onto path. And there we go. Now we have our 6 Sankey lines. All right, so let's figure out what happened. So we know why we had to remove the side field, because that was kind of breaking our polygon into 2 polygons, which we didn't want. But how did the path field fix our viz? So remember in our densification table, we had t values that went from -6 up to 6 and then repeated in reverse order. The path field, on the other hand, was sequential from 0 to 49. So if you look at this table on the min side, it's going to go from left to right, 0 to 24, then hop to the max line, and then go from right to left back down to 49. And if you look at that on our actual view here, so for line 2, here it's going to start on the min line from 0 to 24, then it'll hop up to the max line to 25, and then it'll go from right to left back down to 49. And because this is a polygon, Tableau automatically connects the first and last point. So the curve calculation is calculating the position of all our points, and then that path field is telling Tableau how to connect them. And that's really all you need to know about polygons in Tableau. You just need to be able to calculate points, and then you need to tell Tableau how to connect them. All right, so as I mentioned earlier, 99% of the time you're going to use that standard model to draw your sigmoid curves, but there could be instances where that doesn't work. So one example that I've seen a lot in recent years is drawing curved lines on a map. So in that case, all the lines are are starting at different points because you're using their location on a map, and then they usually end in like a uniform column or row, and then are aligned to another type of chart, like a bar chart. So in this case, it probably looks something like this model down here. So we're going to have to use this dynamic model. So here's a look at the data that we're going to use in this example. So we have 9 rows, one for 9 different states in the United States. And then we're going to draw curved lines from those states to a uniform column off to the right of the country in the Atlantic Ocean. So we have our states, we have this rank field, we have the latitude and longitude, and then we have just a value column. And then we're going to use this kind of standard densification table that we used earlier that just has the T and path fields. All right, so this next step is completely optional. So to draw these lines, we need the starting latitude and longitude and the ending latitude and longitude. So in our data source, we have the starting latitude and longitude, but we also need the end of those lines. So you can manually add those to your data if you want to calculate them outside of Tableau, or if you have a specific position you want to put them in, you can just include those in your data source. Or there are a number of different approaches you can use to try to calculate them. So we're going to take a look at one of these approaches, which is going to use the point with the highest latitude and the point with the lowest latitude as our kind of bounds, and then evenly space all the points between those. So here are calculations to get those ending latitude and longitude values, and we'll revisit these in just a minute. All right, so if we were to stop here and just plot these points, we would have something like this. So our starting points are in blue in the center of each state. Our ending points are in a uniform column off to the right in orange, and we're using a parameter to decide how far off to the right to place that row of points. So you'll notice here that the top mark over here is at the same line of latitude as our highest point on our map, and the same is true with the lowest point. So let's go back to those calculations. So first, calculating the latitude. So that's going to be the vertical position of each of our points. And there's basically 3 sections to this calculation. So the first part here is a level of detail calculation that's going to return the maximum latitude in our data source. And that's going to serve as kind of our reference point. So if you look at our map here, the maximum value is Minnesota. So that's going to be 46.25 for our reference point. The next section here is calculating the range. So it's using that same LOD to return that maximum value, another LOD to return the minimum value, and then taking the difference of those to get the full range. So that would be the difference of this to this. So calculating this distance, and then dividing that by the number of states in our data source minus 1 to calculate the spacing between each point. And then that range is being multiplied by our rank field minus 1. So if we would go back and look at our data, so for Massachusetts, it's going to be that maximum value, which is 46.25 times 1 minus 1, which is be 0. Yep, so the Massachusetts value would be at the top. For our next one, it's going to be that 2 minus 1, which would be kind of 1 spacing unit, 2 spacing units, 3 spacing units, and so on. All right, and then the calculation for the longitude is much easier. We're just doing a level of detail calculation to get the maximum longitude value, which if we look at our map would be in Massachusetts, and then we're just adding that parameter to it. So it's the maximum longitude plus the parameter. Okay, so now we have the start and the end of each of our lines. So we have all of our inputs. Now there's just a couple of calculations that we need to add. Again, these calculations are completely optional, and how you approach them is going to depend on your use case. Sometimes it's easier to just manually enter those points. But once we have the start and end points of all of our lines, we can build the rest of our calculations. So sigmoid, as always, is going to be exactly the same. Our curve field is going to be exactly the same, except here we're using latitude. So it'll be our starting latitude plus our ending latitude minus our starting latitude times sigmoid, which is exactly the same as the previous examples where we're using the starting and end position. So the main difference between this approach, this dynamic model, and the other approach is what we use on columns. So we can no longer use the T field on columns because we need to use the longitude of each state. So in all of our previous examples, we had T on columns and we were just evenly spacing points between -6 and 6. But we can't do that anymore because each point, each line is going to start at a different point. So what we need to do what we're going to do is calculate create a calculated field that'll evenly space points between the starting longitude point and the ending longitude point. So our point spacing field is just going to be the difference between the ending longitude minus the starting longitude divided by the number of records in our data source. And that'll give us the kind of horizontal spacing unit. And then we'll just take that value, add it to our take that value, multiply it by the path field, and add it to our starting longitude to get the horizontal position. So here, instead of dragging T on the columns, we're going to use our if you're following along at home, click on the Sigmoid Demo Dynamic tab and then the Dynamic Data Source. So instead of dragging T to columns, we're going to drag our long adjusted field to columns. And we're going to drag curve to rows. If you're doing these from scratch, you may need to set the geographic role for these. So on our on adjusted, we right click, go to geographic role, select longitude. For our curve, we'll do the same thing and select latitude. Just drag state onto color, change this to a line. Again, I'm going to drag path to path, even though we don't need to in this example. And there you have it. So now you have your curved lines on a map, and then, there's a lot of other things you can do with this. You could stack this on a dashboard with, a bar chart, or just put some labels at the end. So yeah. All right, so these were just a few examples of things you can do with sigmoid curves, but really the possibilities are just endless. If you're interested in learning more, definitely check out florilegetwins.com. Kevin and Ken are incredible, and everything I know about sigmoid curves, I learned from those guys. So those are all the examples I'm going to cover today, but what can you do with those? So those were some pretty simple applications, but you can do some really cool stuff. So I'm not saying that my stuff is really cool, but if you look at my portfolio, nearly every one of my visualization uses one or more of these techniques. So these top three here all use the techniques for drawing circles and Bezier curves, circles and another type of curve, circles, circles, sigmoid curves, circles, sigmoid curves. Pretty much everything I've built in the last year and a half uses these techniques. And, they're easy to learn, and once you learn them, you can really apply them in a lot of different ways. All right, so that's all I have for you today. As I mentioned earlier, all of this information and more is available on our blog, domorewithdata.com. And if you enjoyed the session or if you have any questions, please feel free to reach out to me on Twitter or LinkedIn, and you can check out my Tableau public profile here. All right, well, thank you, and thank you very much for having me, VizConnect.